Okay, so we're talking about the sampling distribution. And specifically, we're talking about the distribution of the sample means. Right? We're saying that every time we go to collect a data set from the population, we collect a sample of data, we calculate the mean, that's our sample mean. And every time we do that, we get a new sample mean. So that sample mean is itself a distribution. So let me just draw what that might look like. We said that the distribution is a normal distribution. A normal distribution has a mean. Most of the data is at or around the mean, and then it slopes off symmetrically in the two different directions. And so, the distribution of the sample mean is going to look something like this. It's going to follow a normal distribution. That means this is going to give you somewhat of an idea of the probability of drawing any particular sample mean when you go to the field and collect your data. Now, we know that the mean of the sample means, it means we get the expected value of the sample mean is equal to the true population mean. If we wanted to graph our data, the data that we use, we would say that the mean here is 900. So that's the mean. The average, the most likely sample mean that you will get is a number near or on 900. Somewhere right around 900 is the most likely. Or I should say this way. The likelihood of getting a number really close to 900 is high. It's much more likely to get a number that's close to 900 than it is to get a number really far away from 900. So we can even look at the values we got. We got 975, so that's here. 975. 625, that's kind of low. That's our lowest value that we got. We have 1,000. And we got 1,050, or 1,150. That's where our observations landed. If we kept drawing, so let's say I had you draw 4 more balls. You draw 4 more balls, you would get some mean somewhere. Maybe it would be here, maybe it would be up here. But we just kept going. We would keep getting draws, observations of sample means from this distribution. But it's much more likely to get sample means that are really close to 900 than it is to get sample means that are way out here in the tails. Does that make sense? Now, when we look at this, the most extreme value that we got was 650. This is kind of low, actually. We look at this is kind of low. We might be interested to know how low this is in standard deviation terms. So in that case, we would want a z-score to know how extreme 650 or 625 was. This just gives us an idea. All right. Now, how distributed the standard deviation of this distribution is called the standard error of the mean, or it's the standard deviation of the sample mean. And we just calculated it. We calculated the standard deviation of this distribution. And the way that we calculated it, or we estimated it, we should say, is we took the standard deviation of our particular set of data, all right, and we divided it by the square root of our sample size. So let me ask you what your standard error of the means are. And we're going to put that right here in the middle. Okay? We're going to call this S of X bar. Okay? This is the standard deviation of your sample data this is the standard deviation. This is your estimate of the standard deviation of the distribution of the sample mean. Okay? All right. What's your standard deviation of the sample mean?
335.
335. 140. I'm just going to round up.
207.
207. Okay. 202. Excellent. Those are all estimates of the standard deviation of the sample. Okay. Does that make sense? How are we doing? Ready to move on to the next set? The next step is the most important thing that we're going to do today. Is the next thing that we're going to do, and it's going to build on everything we've talked about so far, is hypothesis testing. Okay. Hypothesis testing. Now, so let's take a step back and think about what we're doing. In statistics, what we're doing is we're using data to we use statistics to analyze data to answer questions. You know, I mentioned that in this program we're going to be really interested in looking at the impact of development programs on certain outcomes. The illustration I've used so far is fertilizer. If we had a development program that provided fertilizer to small farmers, we want to know how does that additional fertilizer affect their incomes. Okay. Hypothesis testing is a statistical tool, a statistical technique that we can use to help analyze, to help determine whether or not some change that we observe in our data is what we call statistically significant, whether or not it indicates to us a real difference. We can test hypotheses about our population using hypothesis testing, using statistics. All right, let's go into some detail, and I think it'll be a little bit more clear. But basically, what we're going to do is we can use statistics to perform kind of the scientific method, to kind of to do kind of scientific tests. Okay, what's the scientific method? We make an observation, we ask a question, we form a hypothesis, then we conduct an experiment, and then with our experiment we can reject our hypothesis, or this says accept. We normally would say fail to reject. I'll come back to that in a minute. Then come back and form another hypothesis. So we might say to ourselves, I think that fertilizer increases farmers' yields, and I think that increased yields will mean greater incomes. Okay. So I make an observation, I go to the field, I see, oh, these people are using fertilizer. It would seem as if they have higher yields, so I'm going to then ask a question. When farmers use fertilizer, do they have higher income? Ask that question. Then I will make a hypothesis. My hypothesis is that, we'll talk about this in a minute, I'm going to form a hypothesis, and my hypothesis will be fertilizer does not increase yields. Or fertilizer increases yields. Fertilizer increases income. Now that's something I can test. I'm postulating a hypothesis. Fertilizer increases income. I can test that hypothesis and see whether it's true. That's what we can use statistics for. That's going to form the foundation of our econometric analysis. We're always going to be doing hypothesis tests. All the time, hypothesis tests to figure out whether or not some impact that we think we see in our data is actually happening. If there's really a statistical impact of some development program. All right, we'd use hypothesis testing. All right, very important tool. So let's go into it. Basic idea. Hypothesis testing allows us to test a claim about a population by analyzing sample data. By analyzing sample data to distinguish between results that can easily occur by chance from results that are highly unlikely to occur by chance. Let me make that a little bit more clear. We're blending together some of the concepts we've done so far. First, we want to know something about the population. We want to know something about what's really happening. We want to know, does fertilizer increase yields for all the farmers that use it? What's happening in reality when we give fertilizer to farmers? Right, we want to know what's happening at the population level. We want to know what's happening to the population of interest, smallholder farmers in northern Ghana. Right. And the way that we might look at that is we're going to collect a sample of data from those farmers, and within that sample of data, we want to see, does more fertilizer mean higher incomes? We want to use that sample of data to give us an idea of whether or not fertilizer increases income for the whole population. Okay? And now, if I go, let's say I go to northern Ghana and I collect my data, okay? There's 1 million farmers and I collect data from 1,000 of them. That means I go to 1,000 farms and I ask the farmer, okay, how much fertilizer did you put in on your field, okay? And then what were your yields, okay? And then what was your income? Okay, we've got our data. 1,000 farmers from northern Ghana. If when we look at that data, farmers that use more fertilizer have higher incomes, we have to be able to distinguish something that just happens by chance from something that is really a reflection of reality. So let's say we collect our data, and we find that farmers that use fertilizer, their incomes are 100 Ghana cedis more than farmers that don't. These farmers, their average income is 10,000 Ghana cedis. We find that the ones that use fertilizer, they have 100 Ghana cedis more of income per year. When we look at that, we think, well, okay, I mean, that is more. That is higher if they use fertilizer, but 100, that's not a lot. That might just be by chance. You know, if I go back the next time and I collect another data set, maybe farmers with fertilizer will have 100 less, or 200 less. You know, you have to be able to distinguish between something that's just kind of by chance. Like it just so happened that in this data set, the farmers that use fertilizer have 100 more income, 100 more Ghana cedis income. That is just by chance. Versus something that's really a reflection of reality. So if I go there, I collect my data, and the farmers that have used fertilizer have 100 more, and I'm like, well, that might just be by chance. But let's say they have twice as much income. I think, well, okay, maybe there's something to this. Maybe this is real. Maybe this is something that's true about the population. And so we need to use our statistical tools to determine whether or not that difference is significant. Whether or not that, let's say that 100 cedis or that 500 cedis, however much, you know, I'm thinking two populations, the people that use fertilizer and the people that don't. The people that use fertilizer, let's say their income is 500 Ghana cedis more. I need to be able to tell whether or not that 500 difference is significant or not. Is it a reflection of something that's happening in reality, or is it just by chance? What do you guys think of that? Is this making sense, or is this convoluted? Yeah? It's not obvious. These farmers have 500 more Ghana cedis per year. Is that because of fertilizer? I don't know. Is it that the farmers that use fertilizer really have 500 more per year, or is that just because that just so happened in my sample? We all collected samples, right, from the population. None of our samples were perfect. None of our samples perfectly reflected the true population information, right? We had a sample mean that was higher, a sample mean that was higher, a sample mean that was lower, a sample mean that was higher. So in any one sampling, I don't know, is my, you know, this sample is 70, you know, this one's bigger than this one. how do I know that this 500 difference isn't just because that was the sample that I drew? How do I know that it's real? You see what I'm saying? So we need to do a hypothesis test to figure it out. Now, I want to build our intuition. You remember our z-score? Our z-score told us how extreme a value was. Right? Remember we did that on the board. I said if you have a z-score of 0.1, that means you're really close to the mean. That's not an unusual value at all. Right? But if you had a z-score of 3, that's an extreme value. Very unlikely. Right? Way out in the distribution. Right? So we might be able to, I'm just trying to build our intuition here. This z-score, it communicates to us how likely or unlikely a value is going to be. Maybe we could use that same intuition to figure out whether or not that 500 difference that I'm mentioning, right, I'm saying there's a 500 difference between the farmers that use fertilizer and the farmers that don't. Maybe there's a way that we can use this kind of intuition to figure out whether that 500 is extreme or not. If that 500 difference is really extreme, it's really, really unlikely to see 500 more gonocetes per year if there is no effect. If that's really unlikely, then I might conclude that there's a real effect. I'm going to do this using equations in a minute. I just want to build our intuition. I'm saying that we collect data. We find here are farmers that use fertilizer, or here are farmers that don't use fertilizer. Here are the farmers that do. The farmers that use fertilizer, their income is 500 gonocetes more per year than the ones that don't. So there's a 500 difference. I want to know, is that 500 difference, is that indicative of a real difference? That when farmers use fertilizer, really their incomes is larger? Or is that just because it just so happened that when we went to the field, that was our data? We know that samples aren't perfect. We know that samples don't perfectly reflect reality. So we want to know, is that 500, is that extreme? Is it unlikely, or is it likely? If fertilizer has no effect, then 500 might be really unlikely. If 500 is really unlikely when fertilizer has no effect, then I might assume that a fertilizer has effect, that it has an effect, if that 500 is unlikely. Does that make sense? But if 500 is really likely, even if fertilizer has no effect, if 500 is likely just because of the way the distribution works, then I would not conclude that fertilizer has an effect. Okay. I'm going to continue to try to illustrate the intuition here. And I want to use our distribution. Okay. So let's say that we go to northern Ghana and we collect data on income. All right? And we're going to say that I'm going to do this. We're going to say that the average income is 10,000 gonocetes. Okay? That's the average income for farmers in northern Ghana. All right? And that's the average income for farmers that don't use fertilizer. But then, the average income of farmers that do use fertilizer, let's say, is 10,500. Farmers that use fertilizer have 500 more gonocetes per year. But when you look at that distribution, do you think that this is an unlikely value? This is pretty common. I'd look at that and I'd think, I don't really have any reason to think that that 500 actually means that farmers have more, that they make more with fertilizer. I think it just means that it just so happened that my farmers with fertilizer just have 500 more. And that's a pretty likely thing to happen. But let's say that I go there and my farmers have, the farmers with fertilizer have 13,000. And we're way out here. If you look at that, you see, wow, farmers with fertilizer have 13,000. That's a 3,000 increase. That would put them way out on this distribution. Ah, that makes me start to think, I bet that those farmers, I bet that fertilizer does increase incomes. And why? Well, it's because this is so extreme. Okay. Now, this is not exactly how we do it, but I'm just trying to illustrate the intuition. Does the intuition make sense? Mm-hmm. We're going to find whether or not this difference is extreme enough to constitute me concluding that there's a real effect. All right, let's do it. Let's jump in. Okay. All right, so let's go. Step by step. All right. A hypothesis is a claim or statement about a property of the population. All right. Oh yeah, look at that. Fertilizer increases farmers' yields. All right. So I'm making a proposition about the population. In the population, in reality, fertilizers increase yields. If we gave fertilizer to every single farmer and we collected data on every single farmer, we would find that it increases yields. A hypothesis test is a procedure for testing a claim about a property of the population. I'm making a hypothesis. I'm making a proposal. I'm saying that fertilizers increase yields. Hypothesis is how I go and test whether or not there's any evidence that that is true. All right. What we do when we do a hypothesis, it's more water. Excuse me. Okay. What we do when we do a hypothesis, the hypothesis test, the first thing we do is we need to state our hypotheses. And we always state two hypotheses. We state a null hypothesis and an alternative hypothesis. Okay? A null hypothesis is it is a hypothesis that states that the effect that we think exists doesn't exist. So in our case, the null hypothesis would be that farmers with fertilizer have no more income than farmers without fertilizer. The null hypothesis is basically stating that there is no effect. There is no difference. We start out by assuming the null hypothesis is that there is no impact. And then what we're interested to see is whether or not we can accept or reject that null hypothesis. If we accept the null hypothesis, that means we're concluding that there is no effect. If we reject the null hypothesis, then we can, well, we wouldn't say that we accept that there's an impact, but we would say that we have found evidence for an impact, or we can't rule out that there is no impact. Okay. So we state the null hypothesis, a statement that the value of a population parameter is equal to some claimed value. So a common one we might say is, let's say that the population mean of something is equal to 0. All right. The alternative hypothesis is a statement that the parameter has a value that somehow differs from the null hypothesis. So we might claim, okay, that the population impact is 0, and then the alternative hypothesis might be that the population impact is not 0. It's either greater or less than. Or we might say that the alternative hypothesis is that the impact is greater than 0. That means there's a positive impact. Or we might say that the alternative hypothesis is that it has a negative impact. We basically have two hypotheses. One is that there's no effect. and the other is that there is an effect. Okay. Then we go and we test those hypotheses using the hypothesis test. How you guys doing? You guys need a second? You want to stand up for a second to energize? Or we push through? We've got about 35 more minutes. Okay? Let's push for a minute. Let's push for a minute. Let's get through this. All right. Let's do an example. Okay? We're going to construct a hypothesis test. All right? So imagine that we go to a village in rural Democratic Republic of Congo. I'm just always coming up with examples, and I use a lot of like farming examples because all my research relates to farming in sub-Saharan Africa. So that's just what I think of. That's what I always do. So imagine that we go to a village in rural DRC where farmers have never used fertilizer. We run a development program that provides a random sample of farmers with fertilizer. The average income for farmers that did not receive the fertilizer is $600. Now we want to know if the fertilizer increased their incomes. Okay? So we state a null hypothesis that fertilizer had no effect. That is, the average income for farmers with fertilizer is $600. All right, let's set this up. We've gone to a village. All right? None of them ever used fertilizer before. Okay? We take a random sample of them. Let's say there's 1,000 household farmers, 1,000 farming households. We give 500 of them fertilizer, randomly. Okay? A random 500 of them receive fertilizer. Then we go back and we collect data to see what happened to their incomes, see what happened to their yields. Okay, am I saying yields or income here? I'm saying income. All right. We go back to see what their incomes are. Okay, we look at the farmers that didn't have any fertilizer. They have 600 units of income. Okay, their income is 600. We want to know, did the farmers with fertilizer, did they get higher incomes? And if they did, is it significant? Can we conclude that fertilizer increased their incomes by comparing the people with fertilizer with the people without it? Okay? So, we're going to state our null hypothesis. Our null hypothesis is that there is no effect, which would mean to say that the average, the mean income for farmers with fertilizer is what? If there's no effect. If there's no effect, what would the average for the farmers with fertilizer be? 600. That means there's no effect. That means they have the same average income as the people without it. No effect. Do you agree with that? Are you guys comfortable with that? Mm-hmm. Yeah? Okay. So then we also state an alternative hypothesis. So that is that the average yield for farmers with fertilizer, oh, I have a typo there, is greater than 600. It shouldn't be 50, it should be 600. It's greater than 600. That would be our alternative hypothesis. We would not conclude that farmers with free fertilizer have lower incomes. It might be that they have the same income, but it's probably that they have more. So our alternative hypothesis is that they have more income. Okay? So we have a null and we have an alternative. The null hypothesis is we're assuming no effect, no difference. The alternative hypothesis is that there is an impact, there is a difference. Okay. So now we need to test it. We're going to test our hypotheses. When we test our hypotheses, we draw conclusions about them. The conclusion will always be either that we reject the null or we fail to reject the null. We never say that we accept or conclude the null or the alternative, or say that one is true or false. This is because we have significance levels. So even if we reject the null, there's some probability that it's true. So we never say that we know for sure, because statistics is just not perfect. Because no matter what happens, there's a probability that our conclusion is not correct. There's some chance that our conclusion is not correct. So we never say that the null hypothesis is true or the null hypothesis is false. We always say that we reject the null or we fail to reject the null. Remember, the null hypothesis is that there is no effect. Let me just recap this one more time. we go to a village where none of the farmers have ever used fertilizer. Let's say there's 1,000 farmers. We give half of the farmers randomly, 500 of them randomly, we give them fertilizer. The farmers that didn't have fertilizer, their average income is 600. And then we want to know, did fertilizer increase incomes? So we're going to look at the population of farmers that used fertilizer. Our hypothesis, we're going to say two hypotheses. We're going to say the null hypothesis. The null hypothesis is that there's no effect. That means that we're going to say that the average for the population with fertilizer is 600. That's our null hypothesis. And then our alternative hypothesis is that farmers with fertilizer got more than 600. Okay? Then we're going to use some statistical tests to figure out whether or not we can reject or fail to reject the null hypothesis. If we reject the null hypothesis, that means that we have found evidence that the income for farmers with fertilizer is more than 600. We found evidence that the null hypothesis is not true. If we reject the null, we found evidence that it's not true. We found evidence that fertilizer does increase incomes. That's what it would mean to reject the null. That means we do not have evidence that the null hypothesis is true. We're rejecting it. It's not to say that it's false. We don't know that for sure. But we think that it's false based on our evidence. We have evidence to say that it's not true. So we're going to reject the null hypothesis. The other option is we can fail to reject. That means we don't have evidence. We don't have evidence to say that farmers with fertilizer have any higher incomes than farmers without it. And so then we fail to reject. And we conclude, okay, we don't have any evidence to suggest that farmers have more income with yields. All right? Those are our options. Reject, fail to reject. If we reject the null, that's kind of like saying that fertilizer increases incomes. But we're just not going to say that so strongly. If we reject the null, that kind of means fertilizer increases incomes. If we fail to reject the null, that kind of means that fertilizer doesn't. But we don't say that so strongly. Does that make sense? All right, let's keep going. How do we do it? Okay, actually, real quick first. The reason that we never make absolute conclusions. The reason that we don't say, let's see, when we reject the null, the reason we don't say is that fertilizers increase incomes. The reason we don't say that is because there's always some chance that we're wrong. Okay? This gets us to error. There's two kinds of error in hypothesis testing. All right? So let's just look at this. There's two options. We can conclude, we can fail to reject the null. That's kind of like saying that there's no impact. Right? Fail to reject the null. Or we can reject the null hypothesis. That's kind of like saying that there is an impact. Right? But not quite. There's also a possibility that the null is true. Like in reality, if the null is true, that means there is no actual effect of fertilizer. That's what it means to say that the null is true. There's also the possibility that the null is false. That means that in reality, fertilizer really does increase incomes. Okay. So if the null is true, that means fertilizer doesn't affect it. If the null is true, fertilizer doesn't affect incomes, and we fail to reject, we've made no error. We've actually had it, we're correct. If the null is true, it is correct to fail to reject the null. We want to confirm the null. We want to fail to reject it. But if the null is true and we reject the null, then we have committed an error. We have concluded something that is false. That's called type 1 error. It's possible that when we do our hypothesis test, that we will be incorrect. We will reject the null, but the null will be true. That's possible. let's think about what that would look like. We go to our village, the farmers with fertilizer have 600, they have 600 income. I'm sorry, the farmers without fertilizer have 600 as their income. The farmers with fertilizer have 700 income. And we conclude that we can reject the null, and we conclude that fertilizer increases income. But it might be that was just by chance. It was just by chance that those farmers had more income, that the farmers with fertilizer had more income. It was just by chance. It wasn't because they had fertilizer, it was just by chance. Because when we collect data, sometimes the data's kind of far off. So it's just by chance. That would be a situation in which our conclusion was incorrect. We concluded that there was an impact, but there really wasn't one. All right, that's type 1 error. There's no impact, but we say that there is. We really don't like type 1 error. We really don't. If we're doing policy analysis, let's just think about this. We're doing policy analysis, okay? That's what you're being trained to do. You're going to be hired by a government agency or a nonprofit, and they're going to ask you, does this program have an effect? We're about to spend $1 million on this program, and we want to know, does this program work? You do an analysis and you say that it works. They go and spend $1 million and nothing happens. That was a very costly type 1 error. Because actually there was no impact. You said there was an impact. They spent $1 million and it was wasted. We really don't like type 1 error. It was the same way for researchers when we try to publish papers. We really don't like it when we find an impact and it's not true. So we really don't like type 1 error. Okay, type 1 error is bad. That make sense? Okay. It's another kind of error. Okay, let's go to the other side. It also could be the case that the null hypothesis is false. That means that there's an impact. That means that fertilizer really does increase yields. In reality, the truth is fertilizer increases yields. If it's true that fertilizer increases yields, then if we've rejected all hypothesis, we've made no error. We're correct. We've done the right thing. We rejected the null, and the null was false. We've made a correct conclusion. But what if the null is false? It means there really is an impact. If the null is false, but we fail to reject the null, we've committed type 2 error. So type 2 error is, you get hired by a government or an NGO and they ask you, does our program work? You do a study to analyze the impact of the program. In reality it works, in reality it's great. You find no impact and you say it doesn't work. And they don't implement the program. That would be a type 2 error. Which one's worse, do you think? Which one, what do you think? What's worse?
On a personal level, I feel like the type 2 is worse.
Okay. You think the type 2 error is worse? Okay, any dissenting opinions?
I think 1 is worse.
You think type 1 is worse?
Yes.
Okay, so we have some diverging opinions. Let's see. Why is type 2 worse?
Well, I feel like if you're looking at it from the individual person's perspective, if there's potential to help that person and they can't get it, that's awful. But on his point, if you're a government and you're trying to help people and you have this $1 million that you just wasted on something at the government level, that's awful.
Yeah, right. That's good. What do you think?
Yeah, because the type 1 error is going to bring a huge margin of cost. Like you advise, or say, you advise a company or an organization to do otherwise when in reality it doesn't work, and the pump puts their money into it, and they eventually they find out that this thing doesn't work. You advise us wrongly, so the effects on the company is going to be, or the organization is going to be like, they waste a whole lot of money and they don't get anything in returns.
Okay. Yeah, so I mean, it's hard to say, and it's a matter of opinion. In the profession, we tend to really dislike type 1 error, and we do our analysis taking that in mind. I'll show you what that means in a minute. This means something mathematically in a minute. So one way we can think about it is we can say, well, if we implement something that doesn't work, we've wasted the money and we've wasted the ability to help the people. If we fail to implement a project that if we fail to implement a project that does work, we still have the resources to implement something. That means we can take the resources, develop a new idea that maybe works even better, and then when we go, maybe we'll discover that it works. Because if it works better, it'll be easier to see that it works. But it's not obvious. Because if it takes 3 years to develop a new program, those are 3 years that we didn't help people.
Yeah.
Right? So it's not obvious which one of these two is worse. And there's going to be a trade-off. We actually have some ability to control these errors. Okay, I'm going to show you that in a minute. Okay, but this is interesting and it's important. We have to think about this because we actually decide how much type error we have in our analysis. We just choose it. We choose how much type 1 error. So if you say, I really don't like type 1 error, I do not want to commit a type 1 error, then we will set that error level really low. But if you set type 1 error really low, that means you do not reject that hypothesis unless you pretty much know that it's false. We bring type 1 error down really low. If you make type 1 error really low, you're also going to increase type 2 error. If you make it really hard on yourself to reject the null hypothesis, that's kind of what we're saying. We're saying that, let's put it this way. I was using this example before, right? This is a really extreme value. If I have a really extreme value, that might make me think, okay, I'm going to conclude that there is an impact. Well, I get to decide what constitutes extreme. How extreme? I mean, who knows? I mean, this is continuous. There's no rule as to how extreme. You get to decide how extreme. At what point do you conclude? At what point do you reject the null hypothesis? 10%? 5%? 1%? Maybe if you really don't like type 1 error, then you'll say, I will only accept 1% possibility of a type 1 error. That means I'm not going to reject that hypothesis. I'm only going to reject the hypothesis if I have tremendous evidence that the null hypothesis is false. Just think about this conceptually. If I almost never reject the null hypothesis, that means that I'm failing to reject it a lot. And if I fail to reject the hypothesis a lot, that means there's a lot that's more likely that I'm going to commit a type 2 error. Does that make sense conceptually? So there's a trade-off. It's like, which one? It's not easy. Okay. So all right, we've done a lot of conceptual. Let's keep going. We got 15 minutes. All right, type 1 error. In reality, fertilizer does not increase yields, but in the analysis of our sample data, we find that yields are significantly larger with fertilizer. We reject a true hypothesis. Okay, so I just explained this. We can call it. Okay. All right, we get to control how much type 1 error there is. In our analysis, we call this the significance level. The probability of making a type 1 error is known as the level of significance, or alpha. Okay, we see this all the time. When you write papers in my classes, you will be doing this all the time, setting your significance level. All right, how much type 1 error you're going to have. We usually choose 3 possible alpha values. That is 0.1, which is there's a 10% chance of saying fertilizer does not have an impact on yields when it actually does not. Does have an impact on yields when it actually does not. Right? There's a 10% chance of type 1 error. Or alpha of 0.05, there's a 5% chance of type 1 error. Or alpha of 0.01, there's a 1% chance of type 1 error. And you get to decide what level of error you're willing to tolerate based on your research. based on your research question. The lower the chance of type 1 error, the greater the chance of type 2 error. Okay? These are the conventional ones. In your research, you'll always use these three. Actually, when you're presenting results, you will present whether or not your results are significant at the 10%, 5%, or 1% level. Okay. So you'll indicate at what amount of type 1 error do you consider these results significant or not. All right. So we're going to test our hypothesis. Now, I'm going to erase some of this and illustrate this point. All right, so before, as I was trying to illustrate the intuition, what I was saying is that what we're going to try to do is we're going to see whether or not the data that we observe is so extreme that it constitutes, that it gives us reason to reject the null hypothesis. Right? We're using this concept of an extreme value. Now, if you remember, we were thinking about that z-score. The z-score gives us the number of standard deviations a particular observation is away from the mean, right? And so a z-score of 3 is really extreme, very unlikely. A z-score of 0.1 is very common. Okay? We want to think about that intuition. We're thinking about how extreme a value is. We're going to use something that's similar to a z-score. It's called a t-statistic. And what we do is we form a t-statistic. It's very, very similar to the z-score. We take our mean, our sample mean. So in our minds, in the context of our illustration, our sample mean is the average income of the farmers that use fertilizer. Okay? So that's our sample mean. And then we subtract from it the mean, we subtract from it our null hypothesis mean. So let me draw this on the board. All right, our null hypothesis says that the average income for farmers will be 600. Our t-statistic, which is just calling t, is equal to our particular measurement of the sample mean. So we've collected data from 1,000 farmers. All right? So our sample mean in our data set minus the null hypothesis mean. This is what we've stated. The null hypothesis is 600, so we'll just say 600. All right? Divided by the standard error of the mean. Divided by this number that we calculated. By the standard error of the mean. All right? That's going to give us a measurement of the standard deviations of how far away that our particular sample mean is from the average in the distribution. And if it's far enough away, we will conclude that there really was an impact. We will conclude, well, we will reject our null hypothesis, right? Does that make sense? We're using our intuition, right? If it's extreme enough, if the difference is extreme enough, then we will reject our null. We'll say that there is evidence of a difference.
So, in other words, if it is in the negative, or is it, what is the value of the coefficient, the value of the t? Is it negative or positive? Do we have two values for it?
It could be positive or negative. It wouldn't be both. There's only one value.
Okay, one.
It depends on what this is.
Yeah.
If, let's say our sample mean for farmers with fertilizer is 500.
Okay.
500 minus 600, this is going to be negative.
Yeah.
All right. Now let's think about this. This distribution that I've drawn here, let this be our distribution of the sample mean. Okay? That's what this distribution is. It's a normal distribution. It's a distribution of the sample mean. Our null hypothesis is that the average is 600. Okay? Now, we're going to take our particular observation of the sample mean. And we want to see how far away it is from the mean. Now let's say that our farmers with fertilizer, the average income for farmers with fertilizer is $650. That's not a very extreme value. What would you guess our t-statistic to be? What would you guess our t-statistic to be? This is similar to the z-score. Remember, the z-score is the number of standard deviations. Do you think it's going to be like 3? Or do you think it'll be closer to maybe half? 0.5? What would you guess? What would you guess? Just to... Okay, somewhere, you're thinking it's going to be somewhere between 0.5 and 1. That's an excellent guess. That's not a very extreme value. It's not way out in the edge of the distribution. It's kind of close to the mean. Yeah, that would make sense. A standard, I mean, if you're 0.5 to 1 standard deviations away from the mean, that's not very extreme, right? That means it's actually pretty likely that if this is your distribution, that you would get this number by chance. I don't really have any reason to conclude that farmers have more income with fertilizer. Because if I see 650, well, that could totally happen. I mean, if this is the distribution of my sample mean, that could totally happen. Just by chance. But let's say that my sample mean is 800. What do you think that t-score is going to be? What's that? So what you just said is actually smaller than this one. Remember, the farther we get out into a distribution, the more standard deviations we are away. The z-score is how many standard deviations we are away from the mean. So the farther we are from the mean, the more standard deviations we are away from the mean. So you said this might be 0.5 to 1. That's a good guess for this one. Then what do we think this would be?
3 or more.
Maybe 3 or more. Somewhere around 3. Maybe it's around 3. This one's really far away. This is really extreme. If we saw that number with this distribution, we would say, well, that's really unlikely. It's really unlikely to get a number that big if this is our distribution. If that's the case, we might say, well, okay, I think fertilizer does have an impact. It's really unlikely for that to happen. What do you think? Does that make sense? Do you think it's a reasonable way of making decisions? We get to decide how extreme this value needs to be. That's what we do when we choose the significance level. Is we're choosing how extreme this value needs to be for us to conclude that we can reject the null hypothesis. If we require the value to be really extreme, way out in the tail, then we're usually going to fail to reject the null, which means more type 2 error, less type 1 error. Okay, let's keep going. All right, so this gives us an idea. So basically what we have here, this is just what I drew on the board. We have a distribution where the null hypothesis is true. This is the distribution if the null hypothesis is true. This is the distribution if the null hypothesis if the alternative hypothesis is true. That is, if the mean is larger. Right? So let's say we get a number of 650. It's really close, there's no reason to reject that. But if we get one of 9, oh, so close, look at that. All right, I just made these up. All right, if we get a number of 900, look how unlikely that is if the null hypothesis is true. If the null hypothesis is true, 900 is really unlikely. But look at the alternative hypothesis. If the alternative hypothesis is true, 900 is really likely. That means it makes way more sense to conclude that the null hypothesis is, that the alternative hypothesis is true than it is to conclude that the null hypothesis is true. Does that make sense when I show both distributions? Do you have any questions on that? Okay. All right, so what we do in practice, just tangibly. Oh man, all right, we're so close. What we do tangibly is we calculate our t-statistic, okay? We calculate our t-statistic, and then we look up the value that we find in a t-table, and we figure out the probability of observing a t-statistic as large as the one that we have. It's called a p-value. We gotta finish this. Are you guys okay if we go just a couple minutes over? Just to finish this. This is so good. All right. Okay, so let's go to part C, hypothesis testing. Okay. To make this faster, right there, what you see on that page is you have an empty table, has mean, variance, standard deviation, standard error. All right. We're not going to do this one. We're going to do a hypothesis test for the data that you have earlier. Okay. We're just going to make this faster. But let me just wrap this up, and then you're going to do this practice, and then we'll be done for the day. All right. So what we do is we calculate the t-statistic. This is a number. You're about to calculate it. You calculate the t-statistic. You determine your degrees of freedom. Your degrees of freedom is the number of observations that you have minus 1. All right, so in your case, you have 4 minus 1, so your degrees of freedom is 3. And you're going to compare your t-statistic to the t-statistic values across the row in the table. You find the largest value in the row that's still smaller than your t-statistic value. And then that will allow you to find your p-value. All right, now let me just define your p-value real quick. So where do I have this? P-value is really important. The probability of getting a value of the test statistic that is at least as extreme as the one representing the sample data, assuming that the null hypothesis is true. So basically the point is this. The p-value is the probability that your t-statistic is as large as it is if the null hypothesis is true. That means if your p-value is really low, then it's very unlikely that your t-statistic would be that large if the null hypothesis was true. Which means if the p-value is low, you can reject the null hypothesis. The p-value is your alpha. The p-value is this threshold over which you will conclude whether or not you should reject it, or you should reject or fail to reject the null hypothesis. If you have a p-value of 0.1, that would mean there's a 10% chance of type 1 error, and you can conclude, you can choose, do I reject or do I fail to reject the null hypothesis at 10%? You can conclude that. But we'll do that in an example. All right? So here we go. I'm going to leave this on the board, and then we'll do the practice.